Hello everyone and welcome back to the binary search series. So this is the first practice problem of this series and the problem is called the k weakest rows in a matrix. Let's quickly go through the problem statement. So we are actually given a binary matrix in which 1 represents soldiers and 0 represents civilians, and it is given in the question that in each row all the ones will appear before zeros. So using this information we can say that each row will be sorted in a non-increasing order. Now it is also given that a row I is weaker than a row j if one of the following is true. The number of soldiers in row I is less than the number of soldiers in row j. So if the count of 1 in row I is less than the count of 1s in row j, then row I is weaker than row j. And the second thing which is given to us is that if both the rows have same number of soldiers, then the row with the smaller index will be weaker. Now what we have to do is that we have to return the indices of the k weakest rows, and our answer should be sorted in order of weakest to strongest. Now a very naive and a very genuine approach that might come to our mind is that we will traverse each row one by one. So in the given example, if we start traversing each row one by one, and while we are traversing each row we will keep a track of how many soldiers were there in that particular row or how many one were there in that particular row. And once we have the number of ones in each row, we can easily find the k smallest or the k weakest rows. So once we traverse row 1, we'll keep a track that it had 2 soldiers. Then we'll traverse the complete second row and we'll keep a track that it had 4 soldiers, and so on and so forth. And towards the end we will have an array which will contain the number of soldiers in each row. If we sort this array and return the first key elements of this array, we'll have our answer. Now what is going to be the time complexity of this approach? So in the worst case we are going to traverse each row completely. So why are we going to traverse each row completely? Let's assume that there is a binary matrix given to us which is just made up of ones. There is no zero in that matrix. So each row we will be traversing complete rows to get the total number of 1. So in that case, what would be the time complexity? If there are m number of rows and n number of columns, we will be traversing total m into n cells. So the worst time case complexity would be big O of m into n. So this is the time complexity of a naive approach. Let's try to optimize this. Now we have already established that each row is going to be sorted in a non-increasing order. And so it is following a monotonic trend as we discussed in our previous video. And what we are trying to find here essentially we are trying to find here the last occurrence of 1 in each row. We are trying to search the last occurrence of 1 in each row. If we are able to find the last occurrence of 1 in each row, we can easily determine what is the strength or what is the weakness of this row. Now we know that it is sorted, and we also know that we are trying to search an element. So the approach that comes to our mind is binary search. What if we pick each row one by one and start applying binary search in each row? While applying binary search, we try to find the last occurrence of 1 in each row, and we store this number using this last occurrence or the index of the last occurrence. We can find the total number of 1, and for each row we store that what was the number of ones in that row in an array, and towards the end we'll sort this array and we'll return the first k elements of this array and we'll be able to give our answer. Now let's try to see that what would be the time complexity of this approach. Since we will be picking each element one by one, so obviously we would be traversing all the rows, so that would take m time. But for each row we would be doing a binary search instead of a linear search. And if there are n elements in each row or there are n columns, then binary search is going to take time log of n. So our total time complexity reduces to O big O of m into log n. So that is the approach we are going to follow. So let's try to run this approach on an example. So this is the binary matrix which is given to us. So let's pick row number 1 first. If we have picked row number 1, this is the row. Now what we do in binary search is that we pick the middle element, and the middle element is 0. Now one thing we know is that there cannot be a 1 on the right side of this 0, because it is given that all 1 come before 0 in this binary matrix. So if 1 comes before 0, then definitely there cannot be a 1 on the right side of the 0. And using that logic, we can discard the complete right side of this array. So now we need to do a binary search on the left side of this array, because the right side, we know that we are not going to find 1. So we discard the right side of the array and the pivot element as well, because this pivot element is of no use for us. Now what we do is that we take the remaining array and we do a binary search on this remaining array. So when we do a binary search on this remaining array, we will pick the middle element. So if we are taking the floor as the middle element, then we will pick this element and we check that this element is 1. Now since this element is 1, now the possibility is that this might not be the last occurrence of 1, because after this one there's a possibility that there's another 1 on the right side of this particular number. So if there's another 1, then we need to explore that, because we need to find the last occurrence of 1 in each row. So if we need to explore that, what we'll do is basically we'll do a binary search on the remaining half of the array. So now the remaining half of the array is this. Now we will do a binary search on this remaining half of the array, and we'll obviously pick this element, and we'll see that after we have picked this element, there's nothing remaining on the right side of this array. So there's no remaining half. So obviously if this is the end of the half, or after this there's no remaining array, then this has to be the last occurrence of 1. So this is going to be the answer. So let's try to follow this procedure for one more example. So the two conditions which tell us that there is not going to be any more occurrence of 1, or this is the last occurrence of 1, is that if the next element, if we are standing at 1 and if our pivot element is 1 and the next element is 0, then obviously zeros have started. So this is the last occurrence of 1. Or we know that 1 is coming at the last index of the remaining array. So if we know that 1 is coming at the last index of the remaining array, then definitely we are not going to find any more 1 and it is the last occurrence. So those are the two conditions we check to determine if it is the last occurrence. So again here we will pick the middle element as the pivot. Now the middle element is 1, and since the middle element is 1, we know that this might or might not be the last occurrence. So to determine if this is the last occurrence or not, we check that if there is a 0 on it, if this is the last element of the remaining array, or if the next element to this number is 0. So both the conditions are not satisfied. This is not the last element of the remaining array, and neither the next element is 0, next element is 1. So definitely we need to do a binary search on the right half. So what we'll do is we'll discard the left half along with this pivot, because we have already checked this is not the last occurrence. So definitely there's going to be another last occurrence, so we can discard this pivot because it's of no use for us. Now the remaining array is 1, 0. Now the remaining array is 1, 0. In this, the pivot element that will be picked is 1. So because we are taking floor as the pivot element in case of even number of elements. Now since we have picked 1, so we'll try to check that is it the last occurrence of 1 in this array. If this is the last occurrence of 1, then we can return our answer from here. But if it is not the last occurrence, then we would have to search in the right half of this, do a binary search in the remaining right half again. So one of the conditions that we check whether this 1 is the last element of the remaining array. So this 1 is not the last element of the remaining array. And the second condition we check if the next element to this 1 is 0. Yes, so that condition is satisfied here. The next element is 0, and definitely this 1 is the last occurrence of 1 in this particular row. So what we do is we return the answer from here. So we return the answer from here. And similarly, for each row we'll do a binary search, and after binary search we will have the count of 1 in each row, and then we can finally find our answer. So just to summarize, the algorithm is something like, if we have a 0, then we discard the right hand side of the array. Why we discard the right hand side? Because we know that 1 cannot come after 0, so we do a binary search on the left remaining half. If we have a 1, then there are two things that we need to verify. Those two things will determine whether this is the last occurrence of 1. So we need to see if it is the last element of the remaining array or the next element is 0. If either of the two conditions is satisfied, then this pivot element currently is the last occurrence of 1 and we can return our answer. If these two conditions are not satisfied, then definitely this is not the last occurrence of 1 and there is going to be an answer, and answer is all definitely going to be in the right half, because we know that all the complete left half is going to be 1, but that is not the last occurrence because this end element in itself is not the last occurrence. So what we'll do, we'll discard the left half and the pivot and then do a binary search on the remaining right half. Now one more thing to add here is that what right now we'll do is that we'll add these counter indices to a array and sort the array and return the first k elements of that array. But a more appropriate approach would be that we maintain a priority queue or a heap and we store the k weakest elements or the k weakest rows in that heap of size k. And once we are done traversing, we will have a heap of size k with the k weakest elements, and then we can keep popping the elements one by one and return in the same order. So that is a more appropriate method, but since I do not want to convolute this logic and introduce heap as well here, so we'll simply use a vector. We'll simply use a vector or an array, and towards the end we'll sort the entire array and return the first k elements. Now let's try to analyze the time complexity. So the final time complexity. So we have actually analyzed, or we have already analyzed the time complexity for this binary search. It is going to be, if there are, say, if there are n rows and n m columns, then time complexity for this is n log m. And then what we are doing for each row, we are storing its score, and we are doing a sort towards the end. So since in the array we will have one element for each row, so the total size of that array will be n, and sorting that array of size n will take n log n time. So the total time complexity will be n log m plus n log n. So now that we are done with the discussion about the concept and the time complexity, let's jump to the code. So one feedback which I received in previous series was that coding the solution along with explaining is a little distracting. So people preferred that the solution is pre-written and I just walk through the solution. So I've done exactly that. I'll not code the solution as I go. I have already written the code. I submitted on Leetcode, and I'll walk you through the code which I used. So this is the code which I wrote and submitted. So let's quickly walk through the code. This is our main method that will be called to find the k weakest rows. This is the name of the method is k weakest rows, and obviously one input is the matrix, the binary matrix, and another input is k. Right. So what we do, first we initialize our array in which we are going to store the count and the index of each row. So the first step that we do here is that we initialize an array. This array is basically going to store the index of the row along with what was the count of 1 in that row. So we are going to store it in the format count comma index. Why are we doing that? Because we are going to call the inbuilt sort function to sort our vector or sort our array. And what this inbuilt method does is that it first sorts all the elements based on the first element of the pair, and then the elements where the first part of the pair is equal, those elements are sorted based on the second part of the pair. So what we want to do, first we want to sort all our values on the basis of count, because all the rows which have a smaller count are obviously going to be weaker. Then there was a second condition which said that two rows which have the same count, the row with smaller index will actually be weaker. So that's why when the count is equal, we want to sort it based on the index. That's why we are storing our elements in this format. So we have initialized our count array where we are going to store a pair of count comma index. So once we are done with this initialization, we will pick each row one by one. So we have started a loop that will be picking each row one by one. So for each row, we first initialize the count pair. So basically what we have done, the second element is the index of the row, and the first element is going to be count. So we have initialized as 0. It will be updated once we do our binary search and write our logic. So it is initialized as 0 and we have put the index. Now what we are going to do is that, now what we have done, we have stored the size, we have stored the number of columns for this row in a variable h, so that we don't have to access to get the size, to get the number of columns, we don't have to write this complete statement again and again. We have stored it in a variable. Now these are the two trivial conditions. If these conditions are true, we will not do a binary search. So first condition, if the first element in this row is 0, if the first element in this row is 0, then we definitely know that the count of 1 is going to be 0, because there cannot be a 1 after the 0. So since we initialized it with 0 value already, we do not need to do any updation, and we just do a continue and move to the next row. But in case if the last element of this row is 1, so we know if the last element is 1, then definitely all the elements in this row were 1. So we simply update the count with h plus 1, which is basically the total number of columns. So since it was 0 indexed, because we had to use h as an index, so we have added plus 1 to get the exact count. Now if both of these trivial conditions do not satisfy, then what we do is a binary search. Now this is the complete logic for binary search. So let's go through the, so till here it is binary search, this is the outer loop. So let's go through the logic of binary search. So what we have done is that for binary search, we have defined the two pointers, two extreme pointers. One pointer is placed on the end of the row, and this other pointer is placed on the start. Now very simple binary search logic, we find the middle element and we check what is the value of the middle element. So simply first condition that we discussed was that if the middle element is 0, so basically this is the statement which is specifying when mid is equal to 0. So if the middle element is 0, we can simply discard the pivot as well as the right hand side, because we know that 1 cannot exist after 0, so we have discarded the complete right hand side. Now what were the other two conditions? The other two conditions that we had to check was basically if the mid is 1. In that case, we had to check if this pivot is the last occurrence of 1 or if this pivot is not the last occurrence. So in this case, first condition checks that if the middle element is 1 and if the next element is again 1. So if the middle element is 1 and the next element is again 1, what I need to do, I definitely know that this pivot element is not the last occurrence of 1. So I discard the pivot along with the left hand side and I do a binary search on the remaining right array. Now the second case is that my pivot element is 1 and the next element is 0. If my pivot element is 1 and the next element is 0, I am pretty sure that this is the last occurrence of 1. So if this is the last occurrence of 1, I simply update the count in the count array and I am done with my binary search, so I break the loop and then I'll move on to the next row. So this is the whole logic. Now towards the end, we have simply sorted this because we want the k weakest rows. So we have sorted this in order of count, and in case the count is equal, this will be sorted based on the index, because our, as we discussed, our pair is in the form of count comma index. Now we form a final result, and in the final result, we will store the first k elements. So we have stored the index of the first k elements, and index was present at the second position in the pair. And once we are done with that, we return the result finally. So this is the whole code which I wrote on Leetcode, and I also submitted this code on Leetcode, and as expected, it was accepted. And these are some of the stats which I got after submitting the solution. So I think we have covered everything related to this practice problem. In case you still have doubts, please specify in the comment section and I'll try to solve them. And see you in the next video. Till then, take care and keep learning. Bye bye.